To recap, let's look at some distinctions we've already made at the beginning and then some that we've added in this video. We've already distinguished between populations and samples, between parameters and statistics. P is the population proportion, P hat is the sample proportion. Now we've added the sampling distribution, which is the distribution of a sample statistic, and it has a mean, the mean of the P hats, and a standard error, the standard error of the P hats. Let's also keep in mind that we have some variation. Let's also keep in mind that we have some standard deviation from the population. We'll call that sigma p. And then for the sample we have a standard deviation, SP. Now beyond the standard deviation for a population and a sample, we have standard error, SP hat, which measures the spread in the sampling distribution, and SP hat, the standard error for the sample proportion, which goes with the sampling distribution. So let's just look now at the sampling distribution and its properties. It's going to be a bell curve if we take a large enough sample. It's a distribution of the P hats, that's why I have P hat over here. And it has a mean of the P hats equal to the population proportion P. And then it has a standard error. Here the sigma P hats is going to equal the square root of PQ over N, where Q is equal to 1 minus P. So P is the number of yeses or the number of successes, however you want to look at that, and Q would be the number of no's or the number of failures. Those always have to add up to 1. So if there's a 30% chance of success, there's a 70% chance of failure. A couple of relationships, again, let's just review this. A couple of key relationships. The mean of the sampling distribution is equal to the population parameter. That holds here. We had the mu of the P hats was equal to P, the population parameter. And then the standard error includes N in the denominator. So as N increases, the spread of the sampling distribution decreases. In this video we're going to make the transition to inference, and we're going to look at the sampling distribution of the sample proportion. So a sampling distribution is just the distribution of a sample statistic like the sample proportion. So what happens is, we take a sample, compute the sample proportion or whatever statistic we're looking at, and then plot that sample proportion on a graph. Then we take another sample, compute the sample proportion, plot it. Take another sample, compute the sample proportion, plot it, and then repeat that over and over. A couple of distinctions you need to make. A couple of distinctions we need to keep in mind are we have the population and parameter, P, and the standard deviation of the P's, and we have the sample and the statistics that describe the sample proportion, and then the standard deviation of. A couple of distinctions we need to keep in mind are the difference between populations and samples, all of the data that we're interested in, and a sample or subset of the data from that population. And we have parameters that describe the population, and we have statistics that describe the sample. So the population parameter is P, the population proportion, and P hat is the sample proportion, and P hat is the sample proportion.